Hello, mathematicians. I'm doing this as just kind of a quick little video. I wanted to talk with a little bit more depth about standard deviation. I'm doing this one mostly for a former student of mine who's taken some college courses now and just called me to ask me a question. But maybe some other folks would find it useful as well, especially since I did a video a couple weeks ago just describing the basics of standard deviation, meaning how do you calculate the standard deviation for a given data set at all. This one's more about the broad scale of what a normal distribution is. So, first things first, I just want to remind you of what is actually happening here. A normal distribution is an approximation made when you have a real set of data that follows a binomial distribution of some sort. So, okay, there's a lot of vocab terms there, right? But here's the basic idea is let's say I give a test. I'm a teacher, I give a test. Um, the average score on this test is 50%, which I hope it's higher, but I'm using 50% because that's a fairly easy number to work with when doing some example calculations. Um, First things first, important to note, I suppose, that the mean of the data set, meaning the average, right? We will typically write that in statistics as mu. Um, and so I'm just going to say mu is equal to zero point 0.5 because that's the average, right? 50%. I'm deleting my mu there because I didn't like the fact that it was written in that thick line. I like this thin line better. Okay, so the mu is zero point 0.5, which means that the average score is 50%, right? So this zero point 0.5 is the same as this 50% being our average. What we would then do is we would graph the distribution of scores on this particular test. We don't have to graph it in order to calculate the standard deviation. You could just calculate the standard deviation, but I think this will be helpful to show what I mean by a binomial distribution, because that's a little bit of a vocab word. So let's say there were 500 students in this class, and on this axis, my y-axis, I'm essentially creating a frequency bar chart, right? So this is 10 students achieved this particular score, 20 students achieved this particular score, 30 students achieved, right? So we keep going up: 40 students, 50 students, 60 students, 70 students, 80 students, 90, 100, right? So let's say this is a huge college course. The professor gives a test, and he essentially goes in and says, "Okay, well, what were the score distributions, right?" And so he makes like a little table here. How many students scored between a 0 and 5%? Well, not many students. Hopefully that number is super low. On a normal test, this is my example problem, right? But on a normal test, hopefully there's zero people who score in the 0 to 5% range. But I'm making this example problem, I'm just using 50 all the way to 100, right? Just to make things be a little bit more exaggerated and easier to see here. So over here, how many students scored in the 95 to 100% range? Well, also not many, right? I mean, like I hope a lot of students did, but in general, it's pretty hard to achieve a really high score like that. So as the professor is going through and graphing how many students achieved scores in this range, right? So then they have a 5 to 10% range. Well, they expect that a few more students scored in the 5 to 10% range. And then the 10 to 15% range. Well, probably a few more students scored in that range, right? So this bar chart is showing that it looks like about 12 students scored in the 10 to 15% range, right? And this goes on all the way up to what we would expect is the highest value, meaning the most students scored in the range from 45 to 50% and from 50 to 55%, right? And then after that, when we get up into how many students scored From 60 to 65, we expect it to be a few less, right? I mean, the average was 50%. We expect that's where the majority of students scored around 50%. And obviously that trend continues downwards all the way over to the 95 to 100% range, right? So these are all a bunch of different bar charts. And this blue line that I have already put in the background is the approximation of the trend that those test scores follow, right? The reason that that is so important to us is because we can use the approximation of the test scores that we got, or the approximation of the normal distribution, I should say, just to be maintaining proper terminology here. But we can use that to. I want to get rid of all of this stuff without undoing my line, but I'm fearing that that's going to be hard now. Let me just deselect that if that works. That appears to not work. So whatever, we'll just leave some of this stuff in here. Um, so what we're doing with that then is we're saying, okay, by approximating what all we can actually, uh, I'm getting too distracted on deleting all my lines here. There we go. Okay. What we can do by approximating this is we can analyze trends for normal distributions all over the world, right? And it turns out that all normal distributions, by the way, I don't know if I said this fully or not, a binomial distribution, all that that means is it just refers to all of those bar charts that are on there, right? The normal distribution is this curve that is an approximation of all of those bar charts that we are now deleting because we don't need them anymore because we're using this approximation of the normal distribution. The important thing to note about the normal distribution is that within one standard deviation from the mean will always contain about 68% of the data total. So, for example, I'm going to try to use another um, kind of easy number here for my standard deviation. By the way, the standard deviation symbol that we have agreed as mathematicians to use is the lowercase sigma symbol. Let's make our standard deviation in this case 10%. So notice that I'm going to write that as a whole number again, zero point 0.1 instead of 10%. What that means is that one standard deviation away in the positive direction from 50% is 60%. So I might label this as mu, the mean. This is one standard deviation away. That also means that two standard deviations away is 70%. One standard deviation away in the negative direction then is 40%, right? So that's negative sigma. And then two standard deviations, negative 2 sigma, is going to be 30%, right? Well, it turns out that the percentage of the whole data set, meaning the number of students that are between this point and this point, right? One standard deviation away from the mean on either side, is 68% of the whole data set. So, for example, if you were asked, um, you have a class that scored an average of 50% on a test, the standard deviation was 10%. How many students scored between 40% and 60%? You would just look at this chart and say, oh, well, I'm between one standard deviation away negatively and one standard deviation away positively. I know that that's 68% of the total population. What if you were asked how many people scored between 40% and 50%? Well, that's just half of this, right? It's 34%, right? Um, Same thing over here, 34%. We also know that between two standard deviations away in the negative direction from the mean, so 30%, all the way up to two standard deviations away in the positive direction, 70%, contains 95% of the data from the entire data set. Uh-oh. So 95% is two standard deviations away. So from 30 to 70%. That means 95% of students on this particular exam must have scored between 30% and 70%. right? Which means that if I started breaking down each one of these size locations, I could tell exactly how much was between each one of these, right? So if, for example, I was asked how many people scored less than 30%, well, I know that between two standard deviations away from the mean on both sides contains 95% of the data. I know that then this location over here plus this location over here must be the last 5% of people, right? Which means that that's split between two sides. This side over here is 2.5% of all people in the class. And then this over here is 2.5% of all people in the class. I know similarly, if you do the math on that, that would make this location 13.5%, 13.5% over here, right? So if you were asked how many people scored between 30% and 40%, there's your answer, right? What gets tricky is if you were asked something like, well, how many people scored above a 60%, for example? Then you would have to figure out what is the combined area of these two locations. Well, it's 13.5% plus 2.5%. So that would be 16% of students scored above that mark. One last thing that I'll tell you about is there are times when you are asked for a number that is not directly on a standard deviation line, right? So, for example, you might have been asked how many students scored above a 55%, right? So, you would have to add these two areas plus how much is this? Now, it is tempting to say, oh, well, adding this little amount to our total is just half of 34. But that is not correct, right? Because 34%, as you'll notice, the as we get closer to the mean, our value or our curve is higher, meaning more students were in this location, right? So we can't just take 34% and cut it in half. Instead, if we get a number that is a strange number of standard deviations away, like this one, which in this case was zero point 0.5 standard deviations away, um, so I'm going to say zero point 0.5 standard deviations. This would have been 55% in my example here. Then I have to use something called a Z table, which you can look up online anywhere. I'll do a quick lookup of one right now, see if you can find it. Now, without going into too much depth with this, essentially what you would be looking for here, and what these tables tell you about, is what is the area under the curve at a particular number of standard deviations away, right? So, for example, um, if I am looking at a standard deviation of one away. And by the way, there's I should mention this as well. There's a number of different varieties of Z tables out there. Some of them are referring to different components of this curve. So it is important that you figure out, okay, which particular component am I looking at right now? But this is the tool that you would use to essentially tell you how much area is under the curve for non-standard components of a normal distribution. So what I mean by that is, for example, if you look at this z-score table, um, and again, I know this is a super fast explanation of this, but if we look at this z-score table, you'll see that if I go one standard deviation away, right, this is my one standard deviation mark. If I go one standard deviation away, then from the mean, then I have 34% of the data incorporated by that value, right? So on this table, if I go from 50% to 60%, one standard deviation away, that's about 34% of the data. Some Z tables will actually tell you not going only in one direction, but going in both directions. So some Z table, and this is why I say you just got to be careful with your Z tables, is some Z tables will say instead of giving you one standard deviation away from the mean only in the positive direction, it'll give you the standard deviation, one standard deviation away in both directions. So some of them might say 68% if you go down to the one instead of instead of 34%. But most of them are designed in this way. So with a little bit of work, you can learn how to use those. One last thing that I will say is it is possible to take a normal old TI and graph this. I'm not going to show completely how to do that right now, but just because I don't feel like entering the whole formula into here for a standard deviation. But if you were to look up the formula for a standard deviation and or for a normal distribution, excuse me, and you were to go ahead and enter your mean and standard deviation values into that normal distribution equation, you could actually figure out what the area under the curve was using second calc and going down to the integral shown here, right? And then from the integral format, so I would just hit 7, and then from the obviously you need to have a curve up here. It's going to look like this on your graph. And from there, you would basically enter, well, what values do you want to figure out how much area is under the curve for? So once you entered those, the calculator would just go ahead and figure out. So for example, in this scenario, the shaded part on this table uh, is what you theoretically want to know how many people are within that range. And you can tell that this one's from 0 to a little bit above 1 standard deviation. You would just select where do you want the calculator to calculate the amount of area under that curve for, hit enter, and it would do it for you. So that again, that's just hitting second calc, and you can use that integral button to calculate the area under the curve there. Again, you probably need a little bit more explanation. I'm trying to keep it fairly quick here. But that's kind of a broad overview of how you can use standard deviation to figure out various amounts of a data set that are within certain, in this case, grades for a particular test or something like that. Hopefully that's helpful as a real quick introduction. And I can always upload more videos in the future that will be more in depth, but of course, they'll probably turn into a full course if I do that. All right. See you guys later.